This is a recording for Edexcel Further Pure 1, Coordinate Systems 1, the Parabola and Rectangular Hyperbola. This is section 1.6, Cartesian and Parametric Equations for the Rectangular Hyperbola. Well, we've seen previously that conic sections give us a family of curves, which includes a circle, ellipse, parabola and hyperbola. We've had a quite extensive look at the parabola, and now we're going to turn our attention to hyperbola. In fact, a special case of the hyperbola, as you'll see in a second. So we're not going to look at general hyperbola, it will be just one special type. Remember then that the hyperbola is the family of curves where the plane cuts through both the top and the bottom section of the cone. So it's the only one of the family which has got two paths to it. So it has two branches here and here. The rectangular hyperbola refers to the asymptotes of the curve, and if those asymptotes are at right angles, so we have asymptotes like this, then the curve produced is what's known as a rectangular hyperbola. It's a fairly standard one. You may well have met it before when you've looked at the equation y equals 1 over x. We're going to look at it in a little bit more detail in this video. Well, this is a GeoGebra file which shows us rectangular hyperbola. Here we have the standard equation xy equals c squared. Now you can see that in the case where c is equal to 1, which we have on the screen at the moment, then that would give us xy equals 1, so y equals 1 over x. So this is the equation that we're very familiar with, and this is one of the family of rectangular hyperbolae. What happens if we change the value of c? Well, we can see that if I increase c, then what happens is that the curves move away from the origin, and as c gets smaller, comes closer and closer to, and we're getting, so these are all the same shape, just different gradients coming in. So we've got the standard equation xy equals c squared. Here's an example where we've got c is equal to 2. So we would have xy is equal to 4. Of course, if you wish, you could rearrange that to give you y equals 4 over x. And you can see that that is the same as 4 multiplied by 1 over x. It's a scale factor multiplication of the equation y equals 1 over x. And hence all of the curves look very much the same as each other, just steeper gradients. I'd now like to consider the parametric equations of xy equals c squared. And so we're going to start by introducing a parameter t, and I'm going to let x be equal to c multiplied by t. So that's going to introduce the parameter, but also gives me a way of getting c squared into here. So I can, by substitution, take ct and substitute into this equation here. So you can see that y is going to be c squared over x. So therefore y will be equal to c squared divided by ct. So one of those c's is going to cancel, top and bottom of the fraction, giving you that y is equal to c over t. So the parametric equations are x is equal to ct, y is equal to c over t. And if you combine those, x times y is equal to c squared. So that gives us the Cartesian equation, xy is equal to c squared. So the point xy up here could be written in its parametric form, ct c over t. So a general point on the parameter can be written in that way, as well as just being xy. Well, that's written out neatly for you, so if you don't wanted to pause the video and just have a read through that again, this is the time to do it. In summary then, the Cartesian equation xy equals c squared leads to parametric equations x equals ct and y equals c over t. The asymptotes are the axes, so we have the x-axis or the y-axis as the asymptotes. We can convert from Cartesian to parametric equations very simply because we can use them to calculate the value of c and then substitute into either of the equations that we need. So for example, let's say we had xy is equal to 9. That tells us that c is equal to 3. And so our Cartesian equation xy equals 9 leads to parametric equations x equals 3t, y is equal to 3 over t. That's the end of this particular video. In the next one we'll look at some problems involving rectangular hyperbola.